enough. All right. So we've been talking about solid angle, remember, right? And so the idea with solid angle is that you, to define it, if you want to figure out the solid angle that something subtends, you can imagine drawing a sphere centered on you, between you and that object, and you draw lines from your eye, let's say, to every point on that object, and as those lines pass through the surface of the sphere, they cut out a U-shaped area on the surface of the sphere. Exactly how U-shaped it is depends on, are you standing like this? Are you going like this, right? Different like outlines would show up there. And the area of that outline of you, divided on the surface of the sphere, divided by the square of the radius of the sphere, is the solid angle that you subtend, as seen by the other person. And it doesn't depend on which sphere you pick, because if you make the sphere bigger, the area of that cutout gets bigger in the same ratio as the area of the whole sphere does. And so you'll get the same result no matter which sphere you use. So the solid angle is a property of the thing itself from your location, if you will, as opposed to what sphere you use to define it. So if we want to get fancy and want to start being able to integrate over solid angle, then it is convenient to use good old spherical polar coordinates. And because we are astrophysicists here, we call this angle phi and that angle theta, unlike in your math class where they call this angle theta and this angle phi. Darn it, right? So you all have encountered that before. How many of you have not had like Calc 3 yet, where you do this kind of stuff? Has anybody never seen this before? Everybody has seen it before, is that true? Okay, good, excellent. Then that means I don't have to come up with what it is in the first place. So what we're imagining here is, well, what if I want to talk about a unit of, or a little element of solid angle, again, that I could integrate over, that I could sum over, if you will. And so if we use polar coordinates, then the natural thing to do is to say the z-axis is perpendicular to the surface element, and then the x and y axes are in the plane of that little patch of surface. And we do the usual thing. In other words, imagine I'm talking about some direction in which I am looking, for example, to define b lambda of t, or later we'll talk about I lambda of t if the object isn't a black body. So this is some direction away from the z-axis that we're looking, that lies at an angle theta from the z-axis. And if you project into the xy plane, then the angle phi is the angle from the x-axis over to the projection into the xy plane of that direction in space that we're pointing in. So imagine that we've got the surface of a sphere of some radius r surrounding the origin here. Then if we go back and get you to remember your spherical coordinates, you'll do this in E and M if you haven't already, all this kind of stuff, okay? Then what are the three spherical coordinates? There's theta, phi, what's the other one? R, right? And R is distance from the origin. So here, we're kind of assuming a unit sphere here, but for a second, let's say we're not. Say there's a sphere of radius r. So let's say this is a patch of area on the surface of that sphere, a little patch of area, and the radius of the sphere is r, so this distance is r, and then we want to know, okay, what are some little arc lengths we can sweep out? In other words, what is the area of this little patch right here? What is dA for this little patch right here on the surface of the sphere? So if I imagine, here I am, I'm being spherical coordinates, so here's the x-axis sticking out this way. Actually, I'll put it back here. So, except it's going to be, okay, here's the x-axis sticking out this way, and then here's the y-axis coming this way. Here is the, stop it, here's the z-axis, all right? So here's my arm being the roll of that direction there. Here's my arm. And let's say here's a point right here. Here's the origin. Here's some point right here, distance r from the origin. If I move only in the phi direction, if I drop my arm like this and I swing out a little arc, how far is the tip of my finger moving if it's a distance r from the origin? So really my arm should be at the origin here, distance r from the origin. And I sweep out a little angle d theta like that. So what is this distance right here if I sweep out a little angle d theta, a distance r from the origin? What is that little arc length right there? Crickets. What is it? It's r d theta. It's r d theta, right? Because, well, that's how angle works, right? We said that from the definition of angle, we would have said that d theta was this little arc length divided by r, so this little arc length is r d theta. Okay, you mind what I'm telling you? That's r d theta. Okay, a little trickier, this one right here, because when I do that one, now my shoulder's the origin. The other one, I go like this, and I am sweeping out part of a circle whose radius is the radius of the sphere. But when I go in the phi direction, in the azimuthal direction, I'm not sweeping out a circle whose radius is the radius of the sphere. I'm sweeping out a circle which has a smaller radius. I'm sweeping out a circle which is this distance right here, away from, so it's this circle centered at a point along the z-axis. And so even though it doesn't look like it, because it's a perspective drawing, this is a right angle right here. That is a right angle. And the hypotenuse is r, the radius of the sphere. And this distance right here is the side of this right triangle here, right triangle, that is opposite angle theta. So if this distance is r, what is this distance right here? So I have a triangle. This is a right triangle right here. This is a right angle. Hypotenuse is r. Here's angle theta. Side opposite angle theta. SOHCAHTOA. Yeah, it's sine theta times r. It's r sine theta. So this distance is r sine theta. And I'm swinging through an angle up here or up here. This is d phi as well as this is d phi, this angle. R sine theta, sweeping an angle d phi, right? So here's r. Can I do this? Here is r sine theta. Okay, I can do it this way, okay? R sine theta, and I'm going to sweep a little d phi around, no, it's got to be over here. Oh, God damn it. Here, d phi, oh, stop it. Anyway, r sine theta d, what is this distance right here?
R sine theta d.
Thank you, there's r sine theta d phi. So the area of the little patch is r d theta times r sine theta d phi, or in other words, dA is r d theta times r sine theta d phi, also known as r squared sine theta d theta d phi. That's that area of that patch on the surface of the sphere. So then the question is, what solid angle does our kind of rectangular ice cream cone comprise? What is this solid angle down here that is defined by that rectangle of directions, so to speak, right? So you see what I mean by that solid angle? It's this thing at the base here, which would have that rectangular cross-section. Any slicer would have a rectangular cross-section. Well, what is the relationship between area on the surface and the radius of the sphere that It's what's that? Yeah, dA over r squared. D omega is dA over r squared, or in other words, it's going to cancel that r squared right there. D omega is sine theta d theta d theta d phi. That is a super fundamental relationship, that in spherical coordinates, the element of solid angle at the origin, if you look at a solid angle defined at the origin in spherical coordinates, d omega is sine theta d phi. If you make like a little rectangular patch, so to speak, of directions, or a rectangular patch on the surface of the sphere, or a rectangular, if you will, a cone of rectangular cross-section of directions, that solid angle is sine theta d phi. And so that's what this is illustrating. You could also get this from the idea of it doesn't matter what the area of the radius of the sphere is. So for a unit sphere, this patch has area sine theta d phi, and numerically it's the same thing as the solid angle that the patch subtends as seen at the origin. But keep in mind, those are different things, right? The area isn't the solid angle. The solid angle is what that area subtends at the center of the sphere. So if I have on the sphere, if I draw a rectangular patch that spans d theta in latitude and d phi in longitude, so to speak, then the solid angle of that patch as seen at the center of the sphere is sine theta d phi. Okay, are you buying what I'm selling? Have I got you to, like, all right, cool. Okay, so what questions do you have? What might be confusing there? Because we're going to use this now to find the relationship between flux and specific intensity. So now that our friends at home have seen the figure, I'll go ahead and point to the rest of the board to give myself more room to write here. Yeah, something like that'll do. Okay. The relationship between flux and specific intensity. So, the Planck function, b lambda of t, is independent of direction. i.e., it is isotropic, is the fancy word for that. It is isotropic. So no matter what direction you're considering, thermoequilibrium radiation, which is what b lambda represents, the Planck function, is radiation in thermoequilibrium. It's the same in absolutely every direction. The specific intensity is completely uniform. If you were bathed in thermal radiation at a specific temperature, no matter what direction you looked, everything would look equally bright in that equilibrium situation. To find what we call the monochromatic flux, F sub lambda. So the energy per unit time, per unit area, per unit wavelength interval emitted by the surface energy per unit time per unit wavelength interval such that the total flux, energy per unit time per unit area, is the integral over all wavelengths of F lambda d lambda. So if we actually plot a blackbody curve, a Planck spectrum, what we're going to find is a function that looks like that. Generally, it rises and then falls like that. If the temperature were to increase, what would happen to the wavelength of the peak? Would it get shorter or longer if I increase the temperature? What does Wien's law say?
It's going to get shorter.
It's going to get shorter. So if I increase the temperature, the peak wavelength gets shorter. What happens to the, if you will, brightness at every wavelength as the temperature gets up, right? So if I increase the temperature for a different T, this curve would get taller everywhere, and also the peak would shift to the left further and further as the temperature rose. So we're looking for an expression for F lambda in terms of B lambda, and the total flux from the surface is the integral of F lambda d lambda. In other words, here's a little wavelength interval, d lambda. So this is, on one side it's lambda, on the other side it's lambda plus d lambda. F lambda d lambda, that little area right there, is the energy per second, energy per unit time per unit area, with that is 4 wavelengths in this little range from lambda to lambda plus d lambda, right? So F lambda d lambda equals energy per unit time per unit area for photons in wavelength range lambda to lambda plus d lambda. F lambda d lambda is that. So F lambda itself is energy per unit area per unit time per unit wavelength interval. So if I multiply by a little wavelength interval, I get energy per unit time per unit area, 4 photons in that little wavelength range. So energy per unit time per unit area, what would that be? SI, energy per unit time is SI. What unit is that? What's the SI unit of energy? How do you, yeah, joules, right? SI is joules. Time, what's the SI unit of time? So joules per second, what do we call that? Watts, right? Watts per unit area is SI square meters, right? So this will be watts per square meter. Watts per square meter is what F lambda is, what F is, I meant to say. This piece right here is watts per square meter for photons in that wavelength range. This would be the flux coming out of the surface, but only in the form of photons in that narrow range of wavelengths. And the total flux coming from the surface is what you get by adding up for every wavelength. For every wavelength. So the total flux is this integral F lambda d lambda Or in other words, it's the area under the entire curve, which is the total flux coming out of the surface. And F lambda is how much is coming out of the surface per unit wavelength interval, as opposed to over all wavelengths. So F is the sum over all wavelengths of F lambda d lambda. It's the integral of F lambda d lambda. Yes?
So for every radiating body, a diagram would look different because each one of those would have some peak, would have some low.
Yeah, so this is a function of temperature as well as wavelength. And so this would be for some particular temperature. And I think we had, yeah, so here are black body curves for different temperatures. So here would be, this could be F as a F lambda as a function of wavelength for 3,000 Kelvin, for 6,000 Kelvin, for 12,000 Kelvin, and for any given temperature, the sigma t to the fourth, the F equals sigma t to the fourth, that's referring to the total watts per square meter coming out of the surface over all wavelengths included. And what we're looking at when we plot this curve is how that breaks down with wavelength. So in other words, the height of the curve times a little d lambda is how much of that flux is coming in that little tiny range of wavelengths. You're only counting photons in that tiny range of wavelengths. And to get the total flux, you have to add that up over all wavelengths, is the idea. Okay, does that make sense?
Yes.
Okay.
Still getting it, but it does make sense.
Yeah, so that is the idea. Yes?
A side question. If we do this, let's say for a given time frame, would they appear to be moving a little?
So this is a static plot. This is if you have a surface at some temperature and it's an ideal black body emitter, then this is the constant plot of its intensity of its F lambda versus lambda here.
What if it's not a black body?
So if it's not a black body and nothing is, then you could have, for example, this is a plot for for the sun, it doesn't look exactly like this. Okay. Yeah, for the sun, the black thing is more like, it's actually more detailed than this. This is just rough, but yeah. So for the sun, F sub lambda isn't the ideal black body function, but it's still true that F lambda for the sun integrated over all wavelengths is the total flux coming from the surface of the sun. No matter what, integrate the flux F sub lambda, the flux per unit wavelength over all wavelengths, and you get the total flux from the surface. Okay, so what are the units of F sub lambda itself? Well, it's per unit wavelength interval. So the units of F are watts per square meter, but the units of F lambda are flux per unit wavelength interval. Right? So what are the units of flux again? What is flux? It's power per square meter. So flux units are, SI units are watts per square meter, yeah. Watts per square meter. What about the per unit wavelength interval? What are the units of that little wavelength interval? A wavelength is what kind of thing? Is it a time? Is it a distance? Is it a temperature? What is a wavelength interval? Meters, yeah. So it's watts per square meter per meter. In other words, F lambda has units ultimately of watts per cubic meter, but in terms of radiation from the surface, it's really better to think of it as watts per square meter, because it's watts per square meter of wavelength interval. That's really what it comes down to. So it's funny units in terms of watts per cubic meter, strictly speaking, but if you're thinking in terms of radiation from the surface, think of it as watts per square meter per meter, is how to think of it. Okay? What questions do you have? So, yes?
Sorry.
Gosh, no, go ahead, yeah.
When these wavelengths, yes, when those photons reach us, the wavelength, it would have changed by the time it gets to us a little bit,
Why?
because it's traveled across so many light years.
Doesn't care. So, well, it depends on what you mean. So, if you're talking about the expansion of the universe and the cosmological redshift, then that certainly happens. And interestingly enough, it can be shown that if you Doppler shift a black body spectrum, so if you have something giving off a black body spectrum and it's moving, say, away from you so that all the wavelengths get redshifted, the result of that is still a black body spectrum, but at a lower temperature.
Okay.
It's actually still a thermal spectrum, but at a lower temperature. So if we see light from distant galaxies, the light shift, it's redshifted, not by the Doppler effect, but by the expansion of space, but that does the same thing. Effectively, it does the same thing. But if you're looking at a star in our galaxy, there's no cosmic expansion to worry about, because remember, our galaxy is held together by its own gravity, and so it does not participate in the expansion of the universe. Our galaxy isn't getting any bigger. But what does happen is there is motion between us and other stars, and so there's a Doppler shift, and so it either blue shifts or red shifts the radiation to an apparent higher or lower temperature than the actual temperature of the star. But those motions are generally small enough that it's hardly noticeable. That's not a very significant effect. But really here I'm thinking of, we're not imagining that we're moving relative to the source of radiation. We're just observing the radiation coming from the surface. Okay? And so we're going to get this relationship between F lambda, which is the total flux per unit wavelength interval, and B lambda with a specific intensity, which is flux per unit wavelength interval per unit solid angle, per steradian. So we're going between the relationship between how much radiation is going into each little piece of solid angle versus the total amount of radiation being emitted by the surface in all outward directions. What we're going to do is think in terms of there's a certain amount of radiation going into each little bit of solid angle, but I'm going to add that up over every direction to get the total amount of radiation coming out of the surface. And then, because I forgot to do this first, we'll write down the formula for the Planck spectrum, the actual formula, and say, okay, so B lambda is this formula, and F lambda, which you're more likely to encounter in physics 280 than B lambda, is this simple relationship compared to, there's a simple relationship between F lambda and B lambda that we will see here. And then I will remember to say, oh, by the way, here's what B lambda looks like, and therefore here's what F lambda is. Because as I started doing this, I'm like, crap, I don't think I ever wrote down the exact Planck formula for them. But you saw something very similar in physics 280, presumably. You talked about thermal radiation and so forth. Say, okay, so any more? No, it's fine. Any further questions? I like questions. It's good to ask questions.
That's all for now.
Okay, that's all for now. All right. So, to find the monochromatic flux, energy per unit time per unit wavelength interval emitted by the surface, where F is the integral of F lambda d lambda, and then, so just next to it in my notes, right, so I just spent 10 minutes going in that little space right there. In terms of B lambda, in terms of B lambda as a function of t, so this would be F lambda as a function of t in terms of B lambda as a function of t, right? So here I have to insert blah, 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 all that stuff we were saying before. And then finally, here's the sentence. To find the monochromatic flux of F lambda of t in terms of B lambda of t, we integrate over solid angle into the outward hemisphere. So in other words, the picture here is, here's your little chunk of surface, here's a little patch of surface, here is, you can imagine, okay, how much energy, how much flux is going into each little piece of solid angle, and I'm going to add that up for every outward direction. What I want to know is how much total radiation is flowing out of that square, out of that, well, we say square meter of surface into outward directions as opposed to downward, inward directions. Think of it as like at the surface of the star, outward directions. So do you understand what I'm getting at here? If this is a patch of surface right here, the total flux is how much is coming out of that surface. I don't care what direction the photon is traveling when I do that. If I want the total flux, I add up all the photons, no matter what direction they're flying when they come out of the surface. And how I'm going to get that is I know B lambda is uniform. I know that the amount going into each little solid angle when I account for the projected area of the surface is the same, so I add up all of those to get the total amount of energy flowing out of the surface as opposed to how much is coming into each little piece of solid angle. That's what I'm trying to do here. So, how am I going to do that? F lambda, I'll just suppress the t here, will be the integral into the outward hemisphere of B lambda cosine of theta d omega. And again, that cosine of theta is coming from this idea that if I'm looking at an angle to the surface, I just see the projected area dA cosine theta of a patch instead of the entire area of the patch. And so we can think of, remember that dE is equal to B lambda times d lambda dt dA cos theta d omega, right? Remember that whole big string that we multiply B lambda by to get what dE is coming out of our little patch of area dA into solid angle d omega in wavelength range lambda to plus d lambda and so forth. So in other words, I'm trying to figure out what the total flux F lambda is. That'll be, each contribution will be equal to dE over d lambda dt dA, what am I trying to do here? Yeah, B lambda. Yeah, right. So, right, so what I'm going to do here is I'm going to divide through by everything except the cosine theta d omega. I'm going to take this side and this side, divide through everything but the B lambda cosine theta d omega. So on the left-hand side, I've got dE over d lambda dt dA. On the right-hand side, that contribution is equal to B lambda cosine theta d omega. What is dE over dt over dA? What is that unit-wise? What does that represent? We're only looking at what is flowing into d omega. That little bit flowing into that dE over dt over dA flowing into d omega. What are these units here? dE dt is watts per square meter, right? So this is the flux per unit wavelength interval flowing into solid angle d omega. That's what this represents. flux per unit wavelength interval flowing into d omega. So the flux per unit wavelength interval flowing into d omega is b lambda cosine theta d omega. And so if I add that up, I will get what I'm looking for, f sub lambda. Make sense, not make sense, puzzled? What questions do you have? Yes?
Why don't we look at every area element perpendicularly? I understand why we use cosine theta, but why do we have to?
Why do we, so what we're looking at is we want to know how much is coming out of each little piece of the surface. So I'm imagining a little piece of the surface sending this radiation out. If I wanted how much was coming out of the whole star, I'd also have to integrate this over the surface area of the star. But I just want how much is coming out of each little patch on the surface of the star, is the idea here. So this is a per unit area type of thing, because it's the watts per square meter per unit wavelength interval coming out of a local little piece of the surface.
Understood.
Okay, so that's why we need the dA to be part of all of this. But in the end, you let everything shrink to zero when you talk about these kinds of quantities.
Okay, we'll think of it.
Okay, okay. So now we can do the integral. And as I've said, you know, this stuff is subtle, and you need to think about this, at least I sure did, multiple times, and not just when you're in class. This really, you got to think about this very carefully to sort what it all means. Come to your professor if you're like, wait, I got stuck, I don't understand this little piece here. I'm happy to work with you on this. So, what's d omega again? Let's do this as a integral over polar coordinates. So here's the z-axis. What angle's that right there? The whole angle away from the z-axis, not a little increment of it, but the whole angle.
R cosine theta.
No, I just want the angle itself. What is that angle called in spherical coordinates? That's theta, right? That's theta, and we could imagine then also, here's the x-axis, here's the y-axis, that angle right there is the angle phi. So I'm integrating over all theta and phi in outward directions. I'm going to add that up in all outward directions. We know d omega was, what is it again? Burn it into your brain. D omega is
D over R squared.
No, we don't have an r squared here because we've divided through by r squared to just get solid angle. So d omega was yeah, d omega is sine theta d phi. This is sine theta d phi. I'm integrating over the outward hemisphere, only outward directions. So if this table is the patch, here's the z direction. Outward directions are theta goes from what to what? Theta goes from the z-axis to the xy plane and no further, because I only want outward directions from the surface. So that's, this is theta equals what? Along the z-axis, that's 0, up to theta equals pi over 2. Yes. So the theta integral goes from 0 to pi over 2. I'm going to put that one second. Theta equals 0 to pi over 2. So if I consider every possible outward direction, those range from theta equals 0 to theta equals pi over 2. What about phi? Yeah, all the way from 0 to 2 pi for phi. I feel like I'm stirring a cauldron here. All the way from 0 to 2 pi for phi. So integral from phi equals 0 to 2 pi. So this is doing it over the outward hemisphere. It's a constriction on what angles we're talking about, what range of angles we're talking about. B lambda cos theta sine theta d theta d phi Does B lambda depend on theta or phi? Does B lambda care what direction you're looking in? Not for thermal radiation. For non-thermal radiation, it might. Non-thermal radiation can be directional, can be brighter in some directions and not in others. If you look at the screen of an LCD television and you look at it from the side, it starts to look dimmer than when you're looking straight down on it. That's because that's not thermal radiation. The specific intensity is greatest in the outward direction and smaller at other angles, and that's why the screen starts to look dimmer when you look away. That's a symptom of that is not isotropic radiation, it's directional. It's brighter in the outward direction and dimmer as theta gets bigger and bigger. But thermal radiation is the same in every direction, so this would be a good enough approximation. If this was thermal radiation, you see, as I tilt the page, you probably see, well, it keeps looking the same brightness, it just the image gets more compressed because of projection, but it's still the same brightness in every direction. Thermal radiation behaves like that. As you look at the surface at different angles, the surface brightness on your retina stays the same. The size of the image shrinks as you look at different angles because you're getting projection effects, but the brightness per unit area on your retina, the surface brightness on your retina stays the same. And again, surface brightness on your retina is proportional to the specific intensity. So specific intensity is literally what you see with your eyes. That's what you're perceiving. Bottom line is, can I pull B lambda out of this integral? Yes, because it's a constant, so I can pull it out of the integral. And furthermore, remember that if you can factor the integrand in a multiple integral, you can factor the whole integral. In other words, I get to do this. This is a product of something that depends only on theta and something that depends only on phi, namely the phi part. There's no phi dependence in the integrand whatsoever. There's theta dependence because I got cosine theta, sine theta there, but there's no phi dependence, so I can do this. This is B lambda, integral from 0 to 2 pi of d phi times integral from 0 to pi over 2 of cosine theta, sine theta, d theta. I get to do that. I can factor this like that. Go, abandon us all. We'll miss you. Let's take a break now anyway. But this is the exciting development we're at next. Next we'll actually do these two integrals. It's gonna be awesomely awesome, I guess. Yeah. Right? So we can do this factorization. I'll say one more thing. So what is this integral right here? 0 to 2 pi of d phi. 2 pi, yeah. So this turns into 2 pi b lambda times this sine theta cosine theta integral. 0 to pi over 2 of cos theta sine theta d theta, which is begging us to do it by substitution. And we've got two equally good choices, but we're going to make the standard choice because it's the one that shows up most often as being useful. Okay, so if you have my notes, I'm going to change what I have in the notes because I'm going to make what's actually the standard substitution for whatever reason. I didn't do that in my notes. Because here, you know, we can either substitute like, u equals cos theta or u equals sine theta. In astronomy, we usually call, and sorry about this, I know we've said mu is the reduced mass. In other contexts, we use it to mean the cosine of theta, the cosine of the angle between the outward normal to a surface and some other direction that we are interested in. So we say, okay, let mu equals cosine theta. And for those of you who've done a research project with me before, and we talk about limb darkening and so forth, limb darkening functions are usually written as a function of mu, the cosine of the angle between the outward normal to the star surface and the direction of your line of sight to that piece of the star surface. So this is a very standard definition. Mu is the cosine of theta. So if this is a star and we look at a perpendicular to the surface here, and here's our line of sight from Earth, then there's theta right there, the angle from the outward normal is theta, and mu is the cosine of theta. In terms of doing our integral here, mu is cosine theta. So what's d mu? Minus sine, right? Cosine differentiated to minus sine. D mu is minus sine theta d theta. And now we also have to substitute for the limits. When we do an integration by substitution, as I was saying to lots of people in my office hours, talking about that time average integral there, when you do it, when you change variables in an integral, if it's a definite integral, you also have to substitute for the limits, right? So the original integral is theta equals 0 to 2 pi. The new limits are mu for theta equals 0 and mu for theta equals pi over 2. So the new limits are mu evaluated at theta equals 0. So that'll be cosine of 0. What's the cosine of 0? 1. And mu evaluated at theta equals pi over 2. So we're looking at cosine of pi over 2. What's the cosine of pi over 2? 0, right? And so when we do this integration by substitution and substitute for the limits as well, we get that f lambda, which is what we're trying to find here, right? So notice this was f lambda. F lambda is 2 pi b lambda times the integral from 1 to 0 of minus of mu times minus d mu, right? Because sine theta d theta is minus d mu, right? So this is of minus mu d mu when we do the substitution, because sine theta d theta is minus d mu, and cosine theta is mu, so this is the integral of minus mu d mu, which I could certainly just do in this form, but I tend to prefer to get rid of the minus sign, and if I get rid of the minus sign, what else do I have to do? Flip the limits, right? So this is also 2 pi b lambda integral from 0 to 1 of mu d mu, right? And right, we're all back in Math 110 now, or Math 111, I guess. Is that where you do the integrals or something like that? Yeah, anyway, so what's the integral of mu? Half mu squared, right? So this will be mu squared over 2, right? A value between 0 and 1. So what's that give you? What's the integral? Well, this will be 1 squared over 2 minus 0 squared over 2. Quick, what's 1 squared over 2 minus 0 squared over 2? 1/2. So this is 1/2 of 2 pi b lambda for a grand total of pi b lambda. Pi b lambda. That's kind of, I mean, mathematically here, that's a completely true statement. In terms of Greek letters, it's a completely false statement because it's certainly not true that pi b lambda. Pi is pi, it's not lambda. But yeah, pi b lambda is what we've learned here. Forget all that stuff you learned about. It's pi and lambda, it's the same letter. Yeah, I know, crazy, isn't it? F lambda is equal to pi times b lambda. There's the fundamental relationship. For blackbody radiation, the intensity per unit wavelength interval, which we'll sometimes just even refer to as the intensity, is related to the specific intensity in that it's just pi times larger. F lambda is pi times b lambda, after all that. That's for thermal radiation, for isotropic thermal radiation, but again, in general, radiation isn't isotropic. If something isn't a pure blackbody emitter, its radiation isn't isotropic. But for pure thermal radiation, it's isotropic, and F lambda is simply pi times B lambda. And in general, if the radiation is isotropic, even if it's non-thermal, F lambda would be pi times B lambda. Because notice, we didn't say anything about the actual functional form of B lambda here. All we said is that it's isotropic, so we could pull it out of the integral. So this relation would hold for any isotropic radiation field. Tell your parents. You know, for any isotropic radiation field, I can show that F lambda is pi B lambda, and they'll be like, now I know why we're paying tuition, right? So, what questions do you have? Yes?
Why does it need to be cosine theta?
I'm sorry, why did we do what?
Why did we take me to be cosine theta?
For no reason other than you will see that we're going to do other so-called moments of the radiation field, and the standard substitution and definition is mu equals cosine theta there. Yeah, so we could certainly have used sine theta instead. Yeah, there's nothing stopping us from doing that other than mu equals cosine theta is a very standard definition because it turns out to be more useful in other contexts than mu equals sine theta. We'll see situations where mu squared will show up instead of just mu and stuff like that. So later on we'll see why mu equals cosine theta is convenient for a wider range of contexts than mu equals sine theta is what it comes down to. Because we'll see other integrals where it's cosine squared theta that's showing up, and so on and so forth. Yep.
And in the minus mu, is that supposed to be d mu or d mu?
Thank you. It most certainly is supposed to be d mu, yes. Yeah, I demoted my mu to a u by taking off one of its legs. That wasn't very nice of me. But yeah, it's definitely supposed to be d mu. Thank you very much, yes. I always appreciate when it's easy to make a mistake like that up here, so I appreciate when you point out something like that. Yep. Yeah, don't assume that I didn't make a mistake. If for something like that, no, I probably did. Yep. There's a lot of pressure up here because y'all are so vicious and you just won't give me any, no, I'm just kidding. But anyway, give me a break. Stop being so, no, just kidding. Okay. So, as you are happily showing in detail in the homework, right? Well, actually, I'll say this in a minute. So, now, back to page 26, which I accidentally skipped. I jumped right to page 27 in my notes, forgetting that I really should have talked about this too. The actual functional form of the Planck function. Is given by, here's what it actually looks like. B lambda of t is equal to 2hc squared over lambda to the 5th power over e to the hc over lambda kt minus 1. That's the actual function that has doink, 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 doink. That's the actual function that produces these shapes of these curves. If you plot that function for different temperatures, you get these curves. That's what it actually looks like. And now we know that F lambda is pi times B lambda. So F lambda as a function of t is just put a pi in there as well. F lambda is 2 pi hc squared over lambda to the 5th e to the hc over lambda kt minus 1. And when you talk about blackbody radiation in physics 280, that's the formula that you'll see. In physics 280, you talk about F sub lambda, the flux per unit wavelength interval, but we've gone a step beyond that. We've raised our sophistication to consider not just radiation summed up from all directions, but being able to talk about radiation in specific directions with the specific intensity. That's why it's the specific intensity, because you can talk about radiation in specific directions. And that gives us B lambda, which doesn't have the factor of pi in it. For isotropic radiation, there's always just that factor of pi between the specific intensity and the integrated over the whole outward hemisphere flux per unit wavelength interval for any isotropic field, including blackbody radiation. But in general, it's more complicated than that. It's not just a factor of pi between them, because we would actually, in that integral, not be able to pull the B lambda out, because it would have some, or the I lambda, the specific intensity out. B lambda specifically for blackbody radiation, but in general, it's I lambda that we call it instead of B lambda. And if that depends on theta and or phi, you can't pull it out of the integral, and so you get a different result when you compare the two to one another. Right? So for sophomores, for we who have moved beyond sophomores, we have our new version here. So the next time you see a sophomore, unless it's Willow, because Willow's learning both at the same time, if you see any other sophomore besides Willow, just kind of, laugh condescendingly at them because they don't know about specific intensity. And maybe they'll learn sometime. So Stefan Boltzmann law says F is sigma t to the 4th, right? Stefan Boltzmann. Okay, but we know that F is the integral from 0 to infinity of F lambda d lambda. In other words, add up F lambda over every wavelength. Find the total area under the curve, and that's the total flux coming from the surface. So it must be that the integral from 0 to infinity of F lambda b lambda is equal to sigma t to the 4th power. And since F lambda is pi b lambda, this says that the integral from 0 to infinity of pi b lambda d lambda is sigma t to the 4th. Or in other words, the integral from 0 to infinity of b lambda d lambda is sigma t to the 4th power over pi, as you joyfully show in this week's assignment. as you joyfully show in this week's homework, if you integrate this, right? If you take the integral of this function from 0 to infinity over all wavelengths and make the suggested substitution and use either Mathematica or what it tells you, use the fact that this certain integral is like pi to the 15th over 5 pi to the 5th over 15 or something like that, you can show that in fact you get sigma t to the 4th power, where sigma is this bunch of constants that will then, you'll see, oh, okay, well, here's the theoretical value of sigma. It's this combination of constants. And if I plug in all the numbers, it should agree closely with the measured value of sigma, which is 5.67 something, something, something times 10 to the minus 8th watts per square meter per Kelvin to the 4th power. So you'll see the theoretical expression for sigma that comes from actually doing this integral, putting what b lambda is into the integral, and actually doing the integral. You will discover after you make the substitution that constant times t to the 4th power drops out, and that constant must be the theoretical value of the Stefan Boltzmann constant. And it's like, you know, it's h, c, something, pi, something. It's a bunch of constants multiplied together, which multiplies out to what it is supposed to, essentially. What questions do you have? Okay, so now I want to talk about color indices. Can I erase this stuff here? Is this killable? Okay, bye. Goodbye. Bloodbath. Oh, I'm sorry. All that lovely writing just gone, I tell you. Color indices. And it dawns on me, I'm going to run and find something in my office. I think they're there, because I want to show you actual filters. All right, we're going to do a little show and tell here. So we've been talking about so far, you know, the magnitude scale. We've implicitly been talking about what we call bolometric magnitudes. In other words, the brightness of the star summed over all wavelengths. But in practice, astronomers generally observe stars and galaxies and so forth through colored filters. And there's a standard system called the Johnson-Cousins UBVRI system, where U stands for ultraviolet, B stands for blue, V stands for visual, which is a greenish color, in fact, because brightness is measured through this filter, are pretty well corresponding to what our eyes see, because remember, our eyes are most sensitive in the green part of the spectrum. So V stands for visual, although I like to say maybe it stands for verde, because very commonly green, right, is verde. So you can also say it's verde, even though it's not really what it is. It works. Red stands for orange. R stands for orange. No, it doesn't. R stands for red, but I don't know about you, this looks orange to me. I don't have an ultraviolet filter, but the I stands for infrared. Here's the infrared filter. How come you can't see through it? Because your eyes don't see in the infrared, although it actually does pass a little bit of visible light. In fact, if I turn on my flashlight here and hold this up to it, can you see that? You can see some red there, right? So a little bit of red does escape through the eye filter there. And so I wanted to bring these here to give you something tangible to know what I'm talking about here. So I'm going to pass these around, show and tell. They have crud all over their surfaces. It's called filter rot. And so I pulled these out of the surface because of the filter rot they developed on them, and bought more expensive ones that are resistant to it. So what's in my CCD camera at Perkins now is filters that are not prone to filter rot. These are very standardized filters. You know, it's colored glass, but it's very specifically manufactured colored glass. You can't make them ever perfectly identical, but they try to make them as standard as they can, essentially. And each one of these is like 250 bucks. So keep that in mind. It's like $1,000 worth of filters in my hand here. Well, now it's about $1 worth of filters because of the filter rot. But in other words, when they were new, right? So carefully pass these around. Everybody can enjoy looking at the filters there as I start talking about them, just to give you something tangible to know what I'm talking about. So, color indices. Color indices are just the differences of magnitudes measured through different filters like that. So there's what we call, for example, the B minus V color index, which is the magnitude through the B filter minus the magnitude through the V filter. The reason they're useful, jumping ahead, is, let's see, hot stars, are they reddish or bluish in color? Bluish, right? So if you look at a hot star through the B filter and through the V filter and compare the magnitudes, and you look at a cool star through the B filter and the V filter and compare the magnitudes, the difference between the magnitudes will be different for the hot star than it is for the cool star. B minus V depends on the star's surface temperature. And you could try to measure the surface temperature using Wien's law or something like that, but then you'd have to have a detailed plot of brightness versus wavelength for that star. Or you just get magnitudes with your photometer and CCD camera or whatever, CMOS camera, whatever, through the B and the V filters, and there are tables which let you link B minus V to the star's surface temperature that yields that B minus V. So it's a much more efficient way to do things like estimating surface temperatures and things like that. So color indices, magnitudes through different colored filters, can tell us all kinds of information about stars and other celestial objects without us having to work that hard, without us having to make really super detailed measurements. Color indices. So far we've discussed bolometric magnitudes. So-called bolometric magnitudes. Which refer to the energy received from the star integrated over all wavelengths. They refer to the total energy received from the star. Integrated, summed up over all wavelengths. But problem is, one, it's awfully difficult to get a single detector that will detect light at all wavelengths and have it be of uniform enough sensitivity and so forth. And two, as I was mentioning, well, it can be very useful to measure through filters and compare the results and so forth. And so astronomers generally pass the light of a star through a standard color filter before measuring the magnitude. It's easier to standardize that way. Astronomers generally pass a star's light through a standard color filter before measuring its magnitude. So we get what we call filter magnitudes. So here is a plot of what we call the sensitivity functions for the UBVRI filter system. So in other words, well, this isn't what we're going to call the full sensitivity function, but these are plots of transmission versus wavelengths. So in other words, what fraction of the photons actually make it through the filter as a function of wavelength. And so if you didn't have any filter at all, this would be a horizontal line at 1. 100% of the lights are coming through, of the photons are coming through. Put the filter in, so for example, here's the curve for the blue filter, and notice that, well, it presses about 70% of the photons that come through at a wavelength of around like 430 nanometers or so, and it does a good job of transmitting light for a range of wavelengths that extend a bit into the ultraviolet and a bit into the green, but it mostly likes to let through photons that are in the blue part of the spectrum. And that's why when you look through that filter, things look blue, because it's primarily letting blue photons through. And you get similar considerations for the other filters as well. Here's the infrared filter's transmission curve, and this particular one, it's saying it cuts off very sharply at 700 nanometers, but a real filter might also extend a little bit into the visible, and also your eye might go a little bit into what's nominally the infrared. So that's the idea there, okay? Questions so far? What questions do you have? Okay, so we want to talk about what we call the sensitivity function. The sensitivity function S as a function of lambda, or just, again, with that funny notation, S sub lambda, which really means S as a function of lambda, gives the fraction of the incident flux that is actually detected as a function of wavelength. And so this won't depend on just what fraction of the photons make it through the filter. It'll also depend on what fraction of those photons are detected by your imaging chip, what fraction make it through the glass in the telescope, and so on and so forth. So anything that could get in the way of you detecting a photon factors into the sensitivity function. So I'm just going to summarize that by saying it depends on the mirrors in the telescope, the detector, the filter, and so on. And really, even though we won't dwell too much on this here, a big deal has to be made out of standardizing results. And so it's not enough to have identical filters. You'd also have to have identical detectors, identical everything for two observational systems to produce exactly the same results when you're looking at the same star. Well, the atmosphere also plays a role and so forth. So a lot goes into trying to account for all these effects. But the first step is to have filters and detectors whose characteristics are matched pretty closely to this so-called mythical standard system that describes how photons should be detected as a function of wavelength. Lots of details there that will kind of sweep under the rug. Just in general terms, there's a lot that goes into determining the sensitivity function. If we were above the atmosphere, we wouldn't have to worry about the atmosphere, but on the ground we do have to worry about the atmosphere. So there's, astronomers, we have a love-hate relationship with the atmosphere because it blurs stars, it absorbs light from stars. On the other hand, we have to appreciate the oxygen, right? So we have to deal with the atmosphere because we also like to be alive, but we also like to put things in space to avoid these problems. So, the magnitude as observed through, for example, the V filter the green filter there, the visual filter, the verde filter, is then and somewhat confusingly, we call the magnitude as measured through the V filter V. So you have to know from the context, is V the name of the filter? Is it the magnitude measured through said filter? Excuse me. What is it? Well, here it's the magnitude measured through the filter. So it'll be from the magnitude scale, remember that we have this minus 2.5 times the base 10 logarithm of the intensity ratio for two stars is the difference in their magnitudes. And so we're putting that here, minus 2.5 log 10 of the total amount of energy that we're getting through the V filter. So in other words, the integral from 0 to infinity of f lambda S sub V as a function of lambda, so the subscript there says the sensitivity function for the V filter, d lambda. So how much light f lambda d lambda is impinging on the filter times the fraction of that light that actually gets detected, that's the sensitivity function, is the total amount of energy we'll observe through the filter. So that integral plus, and I have to write it here to avoid the camera having it being hidden behind the screen, plus what we'll call C sub V, where C sub V is a constant. And that's because remember that the magnitude scale only defines differences in magnitudes itself, right? We said that M2 minus M1 was minus 2.5 times the base 10 logarithm of F2 divided by F1. But this only tells us the difference in the magnitudes. It doesn't tell us what either magnitude is. And so we have to have a 0 point. For each type of filter, we have to have some definition of, okay, what is 0 magnitude through that filter? And that's where this constant comes in. This constant lets us define what flux through the V filter do we call 0 magnitude. You have to have that calibration before then you can actually get specific magnitudes for things instead of just difference in magnitudes for different stars. You have to have standard stars where you decide this star is of 0th magnitude before you can say, well, this star is of magnitude 2.6 or whatever. Otherwise, all you'll be able to say is the difference in the magnitudes of those two stars is 2.6. Does that make sense, what I'm saying here? You need to calibrate. And this is for the calibration. This would be a calibration constant there. So the value of CV can be chosen so as to define what constitutes a 0th magnitude star. And so we talk about 0 points. What constitutes a 0th magnitude star as seen through that filter. And in the homework, you'll be asked to look at the light coming from, I think it's Sirius, through the B and the V filters and determine whether more light's coming through the B filter or more light's coming through the V filter, that sort of thing. Actually, it might be Vega. Because, roughly speaking, as I've mentioned before, we define the star Vega to be 0th magnitude through every filter. And at first you might think that we're saying that that means that Vega is equally bright through every filter, but it doesn't mean that. In other words, we're just defining these constants to essentially make Vega, it's a little more complicated than that, but essentially make Vega be 0th magnitude through all the filters. There's no implication that the brightness of Vega is the same through all the filters. We're just making different 0 points for different filters for convenience. And so you can't directly compare magnitudes through different filters because they have different calibrations, is what it comes down to. So, if we do that, we can say that CV is equal to 2.5 times the base 10 logarithm of the integral from 0 to infinity of f lambda sv of lambda d lambda for v equals 0, for a star where v is equal to 0. In other words, set v equals 0 over here and solve for CV, and that just solve for CV, and that gives you plus 2.5, right? Take the minus 2.5, take it over to the other side. CV is this calculation for a star whose magnitude is defined to be 0 through the filter, and that's roughly Vega. Roughly Vega. The V doesn't stand for Vega, it stands for the V filter, but to a good approximation, you look at Vega through any filter, and we just call the magnitude 0 for Vega. Color indices, right, plural of index, one index, two indices, not two indexes, two indices. Color indices are obtained by subtracting filter magnitudes from one another. So for example, for example, there's a B minus V color index or a U minus B color index. Very often they're in successive filters by wavelength, so to speak. In other words, you could, of course, do B minus I if you wanted to, but usually we keep the two filters kind of close in wavelength, if you, of course, it's passing a range of wavelength, but in other words, we'll do U minus B, B minus V. What would be the next one? After B minus V, what's the next pair of filters that are next to one another in wavelength? U minus V, B minus, V minus, what am I trying to say? B minus V, U minus B, what would be another one you could do?
V minus R.
Yeah, V minus R is another one that gets done often, things like that. But you could make any combination you like. So, since magnitude decreases with increasing brightness, a bluer, and therefore if it's a bluer star, is it a hotter or a cooler star? A bluer, and therefore hotter, a bluer, i.e. hotter star has a what larger or smaller value of B minus V than a cooler star, okay? So it's bluer, it's B-er than the cooler star is. It's B-er than the cooler star is. So it's got more B. What does that do to the magnitude? Does that make the B magnitude, all else being equal, bigger or smaller? How do magnitudes work? Brighter is, for magnitudes, a brighter star has a lower magnitude, right? And so again, sorry, I'm poisoning your mind to accept that magnitudes, you have to stand on your head to understand them. The B-er star is going to be less B, so a hotter star has a smaller value of B minus V than a cooler star. It's upside down than what you would at first think. And so again, there are tables which relate the B minus V of a star to its surface temperature because it's related to it. Bluer, hotter stars have smaller and smaller values of the B minus V color index. For the sun, I think B minus V is plus 0.62 or something like that. Hotter stars have smaller values than that. Cooler stars have larger values than that. There are some stars that are hot enough that B minus V is actually negative. Okay, make sense? Question mark? Okay, now just to kind of, we'll finish with setting up one of the homework problems, and that's as follows. So when you do this integral, to figure out, like, how much light is coming through the filter, it's this integral from 0 to infinity of f lambda, sensitivity as a function of lambda, d lambda. And so if you think about what we're doing here, what that means is, okay, here's lambda. There's this, if you imagine that the star is a simple black body, then here is f lambda for the star. And then the filter transmission function might look something like this. Here is the sensitivity function for that filter. S is a function of lambda. So in other words, it preferentially lets light in through some narrow range of wavelengths. And so to really get this right, you need to integrate F lambda, S is a function of lambda, D lambda. And so, for example, if you're involved in a project that has Kepler stars in it, working with Rachel Rotenbacher, you and Rachel probably got together and numerically integrated the filter functions against blackbody curves in order to obtain your limb darkening, in order to obtain the ratios of the intensities of the star depending on the limb darkening coefficients and so on and so forth. But, on the other hand, if you want to do a homework problem and not be bothered with that, and often in the real world also want to do you're just trying to get a rough approximation and it's good enough, why then you can do what they want you to do in that homework problem, which is, okay, each filter got this sensitivity function, and there'll be like a central wavelength for the V filter. We might say lambda sub V is, and there's different definitions. Lambda sub V could be the wavelength where it transmits the most light. It could also be this weighted average of how much light it transmits for different wavelengths. But roughly speaking, lambda V will be like a central wavelength, approximately in the middle of the filter's transmission curve. And then the other thing you do is you say, I don't want to integrate that, icky. And that's like, there's no analytic simple function to write down though for those transmission curves. It's measured, you'd have to do a numerical integration. So what you do is you say, okay, well there's also a measure of the width of the filter transmission curve, the full width at half maximum. In other words, what's the range in wavelengths over which you go from the central wavelength to where the transmission falls to half of its maximum value. And the difference between those two wavelengths is the FWHM, the full width at half maximum. And you say, okay, let's make a simple approximation where we just assume that the filter transmits 100% of the light between the wavelengths within that full width at half maximum and 0 elsewhere. So S of lambda is 1 over this range of wavelengths from here to here, and 0 everywhere else. 1 in this range of wavelengths, 0 everywhere else. The book will call that the delta lambda for the filter, kind of the range of wavelengths over which the filter is pretty good at transmitting light. So there's delta lambda and the central wavelength. How can I make an approximation to this integral? Well, now, if S is 1 in that range of wavelengths and 0 outside, how do I replace the integral with a good approximation that's much easier to do? We can do it in 2 stages. So in other words, if S of lambda here was just a box function, if S of lambda was just a box function, 100% transmission between, say, lambda and lambda plus delta lambda. If it was 100% in that range of wavelengths right there, or call this maybe, or actually I could put it like, if this is lambda naught, the central wavelength for the filter, and this is like lambda naught minus delta lambda over 2, and this is lambda naught plus delta lambda over 2, and I know I'm going over time, but I'm also helping you with a homework problem, so you don't mind. What could I do to approximate this integral?
Double the lambda naught.
What's that?
Double the lambda naught.
No, I wouldn't double the lambda naught, because this is just some value, and then here's that value minus some range, that value plus some range. But I'm just saying, I am integrating f lambda, s lambda, d lambda. If s lambda is 0 outside this range and 1 inside this range, what happens to the integral? What is the value of that integral between 0 and lambda naught minus delta lambda? 0. What is the value of that integral from lambda naught plus delta lambda over 2 to infinity? What's the value of the integral between that range of values? 0, because this is 0 there. So what can I do to the limits to make things simpler? Yeah, I use these as the limits. It would be the integral from lambda naught minus delta lambda over 2 to lambda naught plus delta lambda over 2 of f lambda times, what's s of lambda in that range? It's 1, right, times 1 times d lambda. So all I need to do is this, do f lambda d lambda for this range, which is still hard because f lambda is the Planck function. It's icky. But typically, the Planck function does not vary much within the filter range. I've greatly exaggerated it here. Within a given filter range, it should really be narrower than this, and the Planck function is nearly constant over the width of the filter's passband. Nearly constant over this range, over the filter passband. Nearly constant over the filter passband. So what do I do next?
Say that it is constant.
Say that it is constant. So what would the constant value be, roughly?
It would be the whole range with d lambda, because you take f lambda out.
So I'm taking f lambda out. What value of f lambda should I use? F lambda is a function of wavelength. What value should I plug in for the wavelength when I evaluate f lambda to approximate its value over the bandwidth of the filter?
The bandwidth of?
What's that?
Lambda naught.
Lambda naught, right. Put in lambda naught. So in other words, this is approximately f lambda evaluated at lambda equals lambda naught. And now, times the integral from lambda naught minus delta lambda over 2 to lambda naught plus delta lambda over 2 of d lambda. So f evaluated at the central wavelength of the filter's passband times the integral of d lambda, right, because I pulled that out, from lambda naught minus delta lambda over 2 to lambda naught plus delta lambda over 2. What's that integral equal to? It's delta lambda, right, because it's a constant, right? It's 1 d lambda, right? I'm just integrating, if I integrate 1 d lambda, I get lambda, right? And then I plug in lambda naught plus delta lambda over 2, and I subtract from that lambda naught minus delta lambda over 2. That's just delta lambda. So in the end, we get the approximation just being the Planck function evaluated at the central wavelength of the filter times the width of the filter's passband is a good approximation for how much light is coming through the filter, because of the fact that the filter passband isn't that wide. These are fairly narrow band filters, so I can get away with just saying, what's the Planck function at the central wavelength of the filter times how wide is the filter in wavelength is a good approximation to how much energy is coming through that filter. In a sense, we're saying, we can just get away with saying like f lambda d lambda as how much energy is coming through the filter. And so you'll do that and you'll discover what filter, I think it's Vega, what filter In fact, I'm almost sure it's Vega. That would be the one that makes sense. I forgot now. But, I said Vega is 0th magnitude at every wavelength by definition, or for every filter by definition, but that doesn't mean Vega is equally bright through every filter. So you can actually figure out with this approximation, which filter is it brighter through, the B filter or the V filter. It's not equally bright through both, even though we call this magnitude 0 through both. Okay. Oh, look, bonus education. I've given you like 16 free minutes now of education, except I ripped you off earlier because I didn't start class on time because of all these other things I was doing. So it's actually kind of a wash, actually. But you spent more quality time with me and with one another. So actually, it's not a wash, it's a victory, he said, hoping they wouldn't start throwing tomatoes at him. But yes.